Hello everyone, I just wanted to talk to you a little bit about using potential energy diagrams in physics. I wanted to talk about the different kinds of questions that they can answer and the questions they can't answer. Now, for example, question they can answer would be, for example, where will an object turn around? Or how much energy do I need to do some task? Questions they can't answer is anything involving time. So anything involving time, generally speaking, energy is not your solution. It's not going to help you figure it out. So you're going to want to use other tools. All right, so without further ado, we'll start thinking about a simple system. First, we'll think about just, a vertical projectile. Well, some sort of projectile system. It doesn't have to be vertical. So for this kind of system, we would plot potential energy on the y-axis, and in this case, since the coordinate of interest in a projectile system is the height, we'll be plotting a y-coordinate. So we're sort of setting up our coordinate system in the usual XY fashion. Okay, so as usual, we can pick wherever we want 0 to be. Let's see. Okay. Okay. We can pick where we want 0 to be. And for simplicity, I will pick 0 to be at the origin where y equals 0. So I'm sort of assuming that u is equal to mgy, that the ground is where y equals 0, and that's where we're going to stop. That's where we're going to stop. Have the potential be 0. And we would plot a straight line, and this would have a slope equals mg. And, fun fact, you'll note that this is just the weight. So in general, the force on a system is equal to minus du d, in this case y, the coordinate that we're in. If we're doing multivariable calculus, it's minus the gradient of u. Those of you who don't know what this symbol is, don't worry about it. I'm just writing it there for those of you who've had Calc 3. Anyway, and so you'll notice, so like the force that is creating this potential is gravity. And since that's locally downward, the gravitational force is just minus mg, right? So that's how these two things talk to each other. Anyway, so let's talk about energy. So let's say for our system, this is where we start initially, and we give it some kinetic energy K. So that means the total energy of our system is E equals K plus mgyi. Okay, so let's just say that's this much. This is K. This is, of course, mgyi. So that means this value here is our total energy of the system, and that means that this point where our total energy line intersects the curve, this is what's called a turnaround point. So that means that I can just drop this down to here. This is going to be our Y max. This is our max possible height. Now, obviously, if we threw it sideways, or if we gave it an initial velocity this way, it wouldn't make it all the way up there. But we can say this is our maximum possible height if we threw it straight up and down. So if we wanted to, we could create a brand new, I'll call it a funny potential. So I'm going to create a potential where it looks like this. And if I am starting here with a kinetic energy, with the kinetic energy of this, so that means this is my initial potential energy. Notice I've drawn this sort of sneaky U and X. These are negative values. A negative potential energy is okay. So let's say we get part of that kinetic energy back, and this is the amount of kinetic energy that we have. So I can then say this is our total energy here, and these are our turnaround points. So we're going to stay between here and here. This is the range of values that our particle can take. I could say that we are here instead, so I could pick another one where we're out here. That's our U. Let's say our K gets us up here. So this is our E. So we've again found turnaround points. This is the range of places that we could go. So in our activity for Thursday, we're going to be doing gravitational potential energy, but not the way we've been doing it. We're going to do it far from the surface of the Earth. So one of the plots you're going to be seeing in the activity will look, well, it'll be actually correct, but I'm just sort of going to draw it schematically. So we're going to draw it like this, where this is our distance coordinate, and this is our potential energy. And we're going to have the Earth at this position, and the moon at this position, and the curve is going to look something like this. This one is, the Earth is deeper. I don't like that. This is deeper because this is more mass. And you'll get that, you'll figure that out when you look at the formula. But this is the Earth and this is the moon. And we're going to figure out how much energy it takes to get from the surface of the Earth to the surface of the moon. How much energy it takes. And so there's going to be some energy, some, I'll just sort of say magic energy. And I'm going to draw this like so. there's only a finite window of values that we can get at here. Okay? We need, if this is where our this is where the max potential energy is between the Earth and the Moon. And hint, how are you going to find this? If you think about it and remember your calculus and go back to the first sketch I drew up, you'll answer this question. This is sort of an aside for later, and think about it. Anyway, this is the max potential energy. So we're going to want to get a total energy which is going to be greater than here. So if we are starting, if this position is the surface of the Earth, and so this is where we're starting, and we want to get to the surface of the Moon, at least, either side, we're going to need to get over this hump. We're going to need to get over this hump. So this is, in some sense, this helps us find the minimum kinetic energy that we would need, minimum. But if we just put in too much energy, if we get an energy that's above zero, a total energy that's greater than zero, this will blast off to forever, go infinitely far away. So this is our max energy. This is our K max. So we want energies that fit in this band here, so that we don't go past past the Moon and go off and explore other planets. For this whole problem, we're going to assume that the sun isn't relevant because we're not going that much further away from the sun. All right, that is all I have for you guys. That's just some food for thought to get you guys thinking about this activity we're going to do on Thursday. Thank you very much. Have a good day.